Year 10. So last week we had asked you to answer the questions on page 78 and 79. So if you open up your folders at those pages, we're going to go through these answers. Okay. So question 1, a student is finding out what happens when light goes from water into air. She puts a coin in the bottom of the cup and puts the cup on a table. She walks away until she cannot see the coin at the bottom of the cup. Use what you know about how we see things to explain why she cannot see the coin when there's no water in the cup. So obviously we know that light travels in straight lines and a cup is opaque, so the light's not going to be able to travel through the side of the cup. And this wee diagram here probably helps to show that. So the light that's getting reflected off the coin at the bottom of the cup, if she's moved back far enough, it's not going to reach her eye. Now for part B, and I am covering up this mess on purpose here, but part B, her friend now pours water into the cup while she's looking at the coin. The coin appears. Use what you know about how we see things to explain why she can see the coin when there's water in the cup. So the water has obviously been refracted whenever the light has obviously been refracted whenever it's going from the water to the air, and whenever light is going from more dense to less dense, it bends away from the normal. I think this is actually really part C here, and I tried to draw that here, but you can see I messed it up a wee bit. Tried to redo it, not much better. But what I have tried to show here is that the light was traveling up through the water and then bent away from the normal on the way out and towards her eye. I think my second attempt is actually worse than the first. So that's really the diagrams for part C, but I don't think I actually read over part B. So the light has refracted when going from water to air. The ray of light bends away from the normal. Now, question 2 was actually a wee sneaky wee question. I liked it. So mirages are very common in deserts. You see what appears to be a sheet of water a short distance ahead of you. You don't need to go to a desert to see a mirage. On a hot day, so think about the nice hot days in the summer, you'll often see the same effect on a road. So the road in front of you may appear to be wet or shiny, but no matter how far you go, you never reach the water that isn't actually there. And that's all just because it is an optical illusion. So what we're actually seeing is an image of the sky, which looks like water when it's on the road. So the brain works by assuming that light travels in straight lines. Draw a line to show where the light appears to have come from. So I just drew on a straight line here. Probably would have been better if I had drawn like where that was coming from, like that. Okay. Now, part B, as the light travels towards the road, is it moving into air that is denser or air that is less dense? So we need to think back to our year 9 physics here. Do you remember whenever you were learning about convection currents, whenever you heat up a fluid, the hotter air, if it's air we're heating up, the hot air rises, cold air comes in to take its place. The reason the hot air rises is because hotter air is less dense. So if we have a hot road here, if you think of that like it's a heat source, it's going to be heating up the air just above it. So the air here is hotter than the air up here, which means that the air at the road is less dense. So the hotter air near the road is less dense. Now, I'm trying to hide my answer here. Use your answer to part B to explain why the ray bends as it does. Well, me drawing these lines and it's kind of hidden, this wee bend bit here, but it is there. You have it on yours anyway. As the light's coming in, it's like it's changing medium consistently, but it's not. It's obviously still air, but because the air here is less dense because it's warmer, then that causes refraction to happen. And because as the light is getting closer, it's getting warmer and warmer and warmer, that just keeps happening repeatedly. So whenever the light is going from the more dense to the less dense, it bends away from the normal. So as it's coming in here, it's just constantly getting refracted over and over and over again. And then eventually it starts to, see the way here it's rising up away from the road again? Well, that's it going into the more dense, the colder air. So that's why it has started to like change direction and go back up. So here's the way I wrote my answer for that. So the ray is getting refracted as it goes from more dense to less dense, and then from less dense to more dense. So more dense to less dense is as it's coming in, and then from the less dense to the more dense is as it's moving away from the road again. Now I have an apology for you. This wee extension question down at the bottom of the page, Mrs. Turner's class, Mrs. Turner gave you the equation that you would use to do this. So that is 10Q. 10P, I did not tell you how to do this, so it's fine if you've left this out, okay? But for 10Q, who were doing this question, here's the answer if you want to pause the video and look back at that information Mrs. Turner gave you and mark and correct your work there. But 10P, never worry, unless some of you did give it a go actually, so here's the answers. Apologies about that, I hadn't noticed the question before I asked you to do it. Bad. Okay, then ready to mark and correct page 79. So in question 1 here we had to fill in the blanks. So light is refracted when it passes through a glass block. The angle of incidence, I, is the angle between the normal and the incident ray. The angle of refraction, R, is the angle between the normal and the refracted ray. The ray of light changes direction when it enters the glass block because glass is denser than air and light travels more slowly. The ray of light changes direction when it leaves the glass block because light travels more quickly in air than in glass. The rays entering and leaving the block are parallel. Now, for question 2, this is actually very similar to that little practical that we did, I think it was a couple of lessons ago now, do you remember? We did a wee experiment like this. Now this one here, Deepak has been doing, he's only measuring the angle of incidence and the angle of refraction once. So he's only measuring these ones here, right? These ones here, he's not measuring them, so we're not worrying about them for now. So Deepak has been studying what happens when light goes into glass. He measures the angle of incidence and the angle of refraction. So angle of incidence is the angle of the light on the way in, and all angles are measured from the ray of light to the normal. Angle of refraction is the angle between the refracted ray and the normal. So it's this wee angle in here. So what's the angle of refraction if the angle of incidence is 0? Well, an angle of incidence of 0 means that the light is travelling in along the normal, and we know that light doesn't change direction if that happens, so it's just going to continue along the normal, which means that the angle of refraction is also 0, so that's a 0 there. Which result or results does not fit the pattern? Well, if we look here, the angle of refraction is always smaller than the angle of incidence when light is going in this direction, when it's going from less dense to more dense. And if we look through all of these, the only one where that doesn't happen is this third one down. So the one that was an angle of incidence of 30 degrees. And then C, again, don't worry if you didn't get this because I hadn't mentioned refractive index to you. So Deepak replaces the block with one that has a lower refractive index. Write a prediction that he could make about what will happen to the angle of refraction. Well, a lower refractive index means that the light won't refract as much. So that means the angle of refraction will be higher than the results that he got in this table here. So I want to kind of show you what I mean. So if the light was originally, see the way I'm lining up my ruler here with the incident ray, if this block wasn't here, this is the path the light would take. But if he had one with a lower refractive index, it just wouldn't refract as much as being the whole way over there, so maybe about there somewhere, and that means the angle of refraction is bigger because it's measured from the normal. Okay, if you turn over to page 80, we're going to be looking at one special case of refraction today. Now, so far all the experiments that we have done have been looking at light going from less dense air into more dense glass. Today we're going to have a wee look at what happens whenever the light is going in the opposite direction. So we're going to aim our light and we're going to be looking at the light going from the more dense glass into the less dense air. Now, I'm not going to bother reading through this, you can read it, but you'll see the apparatus as I'm using it. One wee clever thing I want to point out here, we use this little shape, it's this here, right? So we use a wee semicircular glass block for this, and we aim our light towards the centre, and then that means that on the way in to the glass block, because we're not looking at the refraction happening here, it's this side that we're going to be looking at, it means that the light's never going to change direction on the way in. So whenever I'm doing this, you'll notice that I'm being like super careful about aiming my light right towards the center of that block all the time, because if I don't, then I might mess up my results a wee bit. Okay, so what I need you to do for me now is get either a blank bit of paper or even a bit of lined paper, because I'm going to do this experiment, but I want you to sketch out like what I have on my page basically. Okay, so pause the video, get yourself a blank bit of paper or a bit of lined paper, a ruler, protractor and a pencil. Okay, so just like the last time, I'm just going to follow the method step by step. Now you might notice I have these ticked already. It's because I'm an idiot and have already recorded this video but messed it up, so I'm having to do it again. So we'll ignore these ticks. I'll do a second tick when I've done them. Okay, so place a semicircular glass or perspex block in the middle of a sheet of plain paper, draw around it, remove the block. Here's my block and I'm going to draw around it carefully. Oh. Okay, so remember you're sketching this on your page as well, so if you do a wee sketch of this as we're going through. So that's step 1 done. Step 2, draw a normal line at the midpoint of the straight side of the block. So remember, the normal is a line at 90 degrees to the surface, and because we have to do this at the center and we need to be really careful about that, I'm going to measure this here. So that is just about 7.8 centimeters. Yeah, is it? 7.7. So if I go to 3.8.5, really, I suppose. There, that's my wee center mark. Okay. Then if I get my protractor, can't find it, got it. And remember to be super careful here. I put this little point here on my center mark and I line this line up with the edge of my block. So I'm making sure I'm taking my time to line that all up properly and put a wee mark at 90. Then I can use this to join. And there's my normal marked on. So make sure you're sketching that as well, remember? So draw a normal at the midpoint, done. Use a protractor to draw a line at 30 degrees to the normal and then replace the block. So it's 30 degrees to the normal inside this block that we're talking about. So if I line my protractor up super carefully and go to 30 degrees, do a wee mark, then this is where I'm going to be aiming my light along. Okay. Oh. So if I go back to my instructions, use a protractor to draw a line at 30 degrees of the normal, replace the block. So I'm going to set this on and I'm going to spend a bit of time making sure that I have it on right. Okay, now I'm going to have to be super careful not to nudge that. So that is that done. Use a ray box with a single slit to shine a ray of light along this line. Right, so I've turned all the lights off, I've closed the curtains, but it's the middle of the day, so I haven't actually been able to get it very dark in here, but we'll still be able to see. It is obviously just a wee bit easier in the proper dark. So I'm aiming my light and I'm taking my time to make sure that I'm got my light going along the center of this line and that I'm aiming it towards this little center mark. So that was our next instruction, just that, wasn't it? If I try and do this, bet you I nudged something here. Yes, mark the position of the refracted ray. So the refracted ray is the one that has come back out into the air here. I have nudged that a wee bit. Okay, now, do you know what's really annoying, year 10? Whenever I did this yesterday and then noticed my mistake, I got a lovely results. Bet you I mess it up here today. Okay, I'm gonna go with that. So if I put my X's along this line like we did last time, then it means I know where to draw my line whenever I take everything away. So I've got my ruler and I'm going to mark that on. Oh, I nudged my ruler there. I think we're all right. Okay, so that's the path that the refracted ray took. Let's go back to our instructions. So, use a ray box with a single slit to shine a ray of light along this line. Done. Mark the position. Done. Now I have to hide one of my answers here. Measure the angle of refraction. So let's do that. So the angle of refraction is this angle here. So if I be super careful with lining up my protractor, then there we go. Oh, spot on 50 there. So my angle of refraction is 50 degrees. Now I'm going to draw out a wee table for doing this. So whenever our angle of incidence in degrees was, what was it, 30? Our angle of refraction in degrees was 50. So if you draw down this wee table for me. Okay, we're only going to be doing one more value, I think. Now, because we're about to draw some more on, I'm just going to mark on these ones as yellow, because we're going to end up with a few lines all over the place here and I don't want us getting confused. So, there we go. Okay, let's see what's next. Measure the angle, done. Repeat steps 3 and 4 for an angle of incidence of 60 degrees. So the first thing I need to do is to get my 60 degree angle of incidence. So line my protractor up really carefully. Okay, 0 round to 60, and then I can do this. So now I'm going to be setting my glass block on and I'm going to be aiming my light in along this line. Now before we do it, have a wee think. What do we expect is going to happen? Well, let's think it through logically. I'll move my block out of the way so we can see a bit better. So whenever the light is going, because this is the glass and this is the air, so the light is going from more dense to less dense. And you see how it's bending away from the normal? So our angle of refraction is bigger than our angle of incidence. Well, if we've increased our angle of incidence, it makes sense that our angle of refraction will also increase. So we might see that the light ends up bending even further away from the normal. So let's have a wee look and see. Put my block on. Okay. I've got my ray of light ready and I'm going to aim it along this line. Look! Now this I think is really, really cool, right? Don't even try and argue with me. How cool is it that we're shining light through glass and it's not coming out the other side, and it's not like it's that funny translucent glass or anything. It's proper normal glass. So if I'm shining my light through glass and it's not coming out the other side, you have to admit that's cool. So do you see what's happening? The light is actually getting reflected back inside. So there's a term for this. It's called total internal reflection, because it's getting totally internally reflected in the glass. Hopefully that makes sense to you there. Right, so before I mark on my line coming out here, I just want to check, have I lined everything up alright? I think I have. So with our angle of incidence of 60, there is no angle of refraction. The light doesn't come out to the other side, but just for our own interest, I'm going to mark on this ray here, and we should figure out what our angle of reflection is then. So if I mark this on there, well, oh, I've messed up. Oh no, look, didn't I tell you I would mess up on this one? Oh, nightmare. Okay, ignore this wee line here, please. I'm sorry. So you should remember, whenever we were learning about reflection, what should this angle come out at? If our angle of incidence for this one is 60, what should our angle of reflection be? Should be 60. Let's have a look and see. This was the one I got perfectly yesterday, and now I'm going to be raging if I haven't. Just about. I got 61 there, didn't I? Oh no, look. 60. Okay, I can be pleased with myself again. So our angle of reflection here was 60. So discovering this is one of our aims for today. Okay, so whenever our angle of incidence is big enough, no light gets refracted outside the glass block, which is quite cool, and it is very, very useful. Let's go back to our experiment and see what we'll have to do now, because I've got carried away there. So we did that, never took it off. Describe what happens to the ray. So I need you to write this in for me, please. So once we had our angle of incidence of 60, the ray of light does not refract out into the air. It is totally internally reflected inside the glass. Pause, write that in, please. Now, point 9 in this, slowly move the ray box between angles of incidence of 30 and 60 degrees. Estimate the angle of incidence for which the angle of refraction is 90 degrees. This is called the critical angle. So I'm going to put my glass block on. Oh wait, before I do that, I just want to mark these on, because do you remember I said there's lines everywhere here? And I don't want to get all messed up. So the yellow one was the 30, the green one is the 60. So now what we're going to do, we're almost going to be working backwards. We're looking to see what does my angle of incidence have to be that gives me an angle of refraction of 90. Now, getting this angle of refraction of 90 can be tricky, okay? You'll see what I mean, hopefully, because the light, well, I'll start over again there. Whenever I'm here at my angle of incidence of 30, as I increase my angle of incidence, do you see how the angle of refraction is increasing and increasing? Well, eventually it's going to reach a point where the angle of refraction is 90, and past that point, that's whenever the total internal reflection starts to happen. And what we have to do is find that point, but what makes it difficult is you'll notice that this refracted ray keeps getting weaker and weaker and weaker as it gets towards the 90 position. So there'll be a good wee bit of backward and forward here as I find the right position. And it's hard to keep aiming at that centre part. Right, so we're nearly there, look. Right, now what I noticed was that if I put my pencil, see the way you can see that's the ray of light there, because it's hitting my pencil, because it's hard to see, especially because the room is so bright. Let's see. If I increase there to that, do we have any along there? No, we don't, so I need to go a wee bit smaller. Let's see. There, look. I reckon about there is just about, because see, can you see how the light is hitting my finger? This one here. Just about. Oh, I've nudged it. Hold on. Oh no. Okay. I'm going to go a wee tiny bit smaller there. I don't think there's enough of the... There. About there. Look, you can see that. See where it's hitting my finger there? Right, let's go for it. So if I mark on this, and then move everything out of the way, I will be able to measure. Where's my ruler gone? Got it. So much stuff everywhere, I'm very messy. Right, if I mark on, this was my light going in. Here. Okay, don't know if I've aimed that right there. And I measure my angle of incidence. Oh my goodness, you're 10, I've nailed it. I knew it was supposed to be 42. Look, yesterday I got 41. So I've actually done this one a wee bit better today. Yes! There we go, it was worth doing it twice, wasn't it? So, do you see here how my angle of incidence is 42? So many things marked on this. So, this angle of 42 degrees is the angle of incidence that gives us an angle of refraction of 90. So I'm going to actually mark that on in a different colour as well. So I'm going to go pink for this one. So this angle of incidence of 42 degrees give us an angle of refraction of 90. Okay, I can turn this off and put the lights back on now. Okay, so this incident ray here, which has an angle of incidence of 42 degrees, give us an angle of refraction of 90 degrees. So it's the one I've marked on pink. Your colours obviously don't have to match mine. Now, this wee angle here has a special name. It's called the critical angle. Make a note of that, please. All right. So I'm going to write the definition of this here and then we'll discuss it a little bit. So the critical angle is the angle of incidence that gives an angle of refraction of 90 degrees. So for this glass or perspex, it is 42 degrees. So the critical angle is 42 degrees, and that is the angle of incidence, this one, that gives an angle of refraction of 90 degrees. This is an important definition. Now, what else we need to take from this today is that if our angle of incidence is any bigger than that, then no light gets refracted and it all just gets reflected back inside the block. So I'll show you that actually in a little bit. We'll get the definition down first. So write this in for me, please. If the angle of incidence is greater than the critical angle, all light is totally internally reflected. Now this is we're only using this for if the light is going from more dense to less dense. This will not work the other way. Okay, so get that written in. Now I said I would show you that, so let's go. If I set this back up, line everything up, get my light back on, then any angle of incidence higher than this pink line here will give me, do you see how in any of these angles there's no light getting refracted, but as soon as I cross this line, then we have light being refracted out the other side. So any angle of incidence up until that pink line there, this one, up until an angle of incidence of 42, will cause the light to refract the way that we're used to. But as soon as, I'm sliding everything all over the place here, sorry. As soon as we go past that line, then no light gets refracted and it all gets totally internally reflected. That is cool. You can't even pretend that it's not. Now, back to page 81 for me, please. We have finished the experiment. What I'm going to be asking you to do, or to show me, I'm going to ask you to show me your page that you have marked all of this on, because then I know you've got the definition of critical angle, and then what happens whenever your angle of incidence is greater than the critical angle. And I also want you to answer the questions on page 81. So question 1, what was the difference between what happened to the ray at 30 degrees and what happened to the ray at 60 degrees? Answer that in your own words. See for this one though, see for what was the critical angle, can you put down what the size of the critical angle is and then write down what the definition of the critical angle is, and then see if you can summarize what we discovered in that experiment in your own words here. I'm interested to see what we put for that. Okay, so you have to show me that extra page, and then you have to show me, or Mrs. Turner, page 81. Okay, I think that is me then for this week. Give me a shout if you have any questions, or give Mrs. Turner a shout if you have any questions, and we will see you next week.